All right, we want to look at a couple special collisions or kind of edge cases here. This should be real quick and easy. So first of all, for 2D or 3D collisions, just conserve momentum in all dimensions. So it's a lot like when we dealt with projectiles. We did the vertical stuff, we did the horizontal stuff completely independently. Same idea here. So the change in x1 plus px2 plus change in px3, etc. is equal to 0. Change in py1 plus change in py2 plus change in py3, etc. is equal to 0. So in other words, the first object's x change in momentum plus the second object's change in momentum in the x direction, third, etc. is equal to 0. Same thing for y, same thing for if you had 3 dimensions. It's just looking at each dimension individually, do conservation momentum, end up with the results. And at the end, use trigonometry to combine as necessary. So it's just like when we did, like I said, projectiles, and then at the end, if you wanted to find the final speed, you just had to, use the hypotenuse of the x speed and the y speed, combine them. Same thing here. If you want to know the final momentum, just do the hypotenuse of the x momentum and the y momentum. Second, I mentioned this in a previous video, but we've got explosions. This is when 2 or more objects start stuck together and then separate. And momentum is conserved. So it's just the opposite, like if you look back at the perfectly inelastic collision, it's basically just the opposite. You start with them having, being a single object with the combined mass, or the 2 objects with the same initial velocity. Afterwards, they're moving independently. Once you do a couple of these, it's real easy, real straightforward. If you can do inelastic collisions, this is the same, just you're basically flipping the equations and flipping what's initial and final. And those are the special collisions that we have to look at.